Oh wait, that's kind of annoying.
Okay.
Welcome. It's time for astronomy. Who's ready to astronomize? All right.
Stars and stuff. Yep. Okay, so welcome to the 51st Astronomy on Tap, everyone. First, we're going to go through announcements real quick, and then we'll get to our first speaker of the night. If I remember how to do this. Yeah, okay, so you can scan the QR code to follow us on social media. You can also donate to us on Venmo and learn more about AoT. And one follow on social media gets you one free AoT sticker. If you want to look at what the AoT stickers look like, I'm pretty sure they're over there at that table. But trust me, you definitely want one. And of course, always tip your bartenders. We love being able to host us at the Grand Stafford, so please tip. And like I said earlier, you can donate either in our donation box over there or on our Venmo account, AoT_BCS. A $15 donation is equivalent to one free AoT t-shirt. They're over there if you want to have a look at them. We have new designs. Some of us are modeling them as we speak. And on top of that, a $10 donation gets you a free mug, which also over there if you want to have a look before you make the donation. So check out our little table over there. It's got lots of cute stuff. And yeah, if you want to scan the QR code, there it is again. And our next event is going to be October 26th, 2022. Maybe we'll have some spooky themed talks. Hopefully, I think that's what. Yeah, wear a costume too. Don't forget that part. We'll have a costume contest if people actually show up in costumes. Okay, and now it's time for the astronomy picture of the day. I didn't know we were doing this.
I got this.
Yeah, go ahead.
I got this. So what we got here is a picture of a volcano in California. Yep. I'm pretty sure. I'm right.
Who takes this? Does someone want to like say words about it?
Does anyone want to say words about this picture?
Does an astronomer have thoughts about this?
Any astronomer?
Well, I'm an astronomer, but
Yeah, you should have.
I don't have thoughts about this, but it is a really nice picture.
It's like the Milky Way. Look at that.
No comment. No comment. And that's the picture of the day. Okay, and last thing, talk to the local astronomers. We all have glow sticks. A lot of us have AoT t-shirts on, unless you're me and forget every week, and also Kevin too.
Kevin.
Okay, and I believe that's all the announcements. So now we're gonna have our first speaker of the night, which is gonna be Dr. Strigari.
Yeah!
Hiding in the corner back there. Yeah, Louis Strigari is a professor of astronomy and physics at Texas A&M. He specializes in neutrino stuff, dark matter stuff, and a lot of other things that he's probably more qualified to talk about than I am. So here you go. Fun fact. Oh, fact about Louis. He has a dog named Matt. And the dog has a graduation tab because he passed kindergarten recently, right?
I think so.
Here you go. Let me figure out. This is yours, right?
Yeah. A little off center.
Yeah, I don't know how to make it full screen. Do you? How do I make this full? Where's Sylvie? How do I make this full screen?
It just is what it is.
Is this?
I mean, we can
Is
deal
this
with
what
it,
you have to
like,
work with?
It only like half matters what's on the screen anyway, so.
Okay.
That's fine.
Yeah, that's fine. Okay, take it away, Louis.
All right, Louis.
So how long do I go? Like, who do I, just, okay, just yank you off the screen. Hi, everybody. Thanks for the introduction and thanks for coming. So, I'm gonna talk about neutrinos. Yeah. It's certainly a little bit of an interactive talk. And you're going to learn some interesting stuff about neutrinos, interesting stuff about the nearest star to us, which is the sun. Okay. Okay, so here we go. So interactive part number one. What is this? That's the sun, right? And that is not only the sun, but that is the sun in white light or visible light. You can see little sort of granules and spots on the sun, which sort of come from activity happening near the surface of it. But the key point here is that the light that we see coming from the surface of the sun started its journey to the surface in the center of the sun many years ago. Does anybody know how long many is? Millions and billions. Oh, you gotta be a little more specific. The light from that was created in the center of the sun took a journey that started approximately this many years ago. How many is this many? It's just, you gotta be like just kind of close, not even like factors of two. 100,000 is approximately. It's good, close enough for tonight when we've had a couple beers already. All right, so 100,000 or so years ago, the sun, the light from the sun started its journey, or the photons, as the people in the business call these light particles, coming out of the center of the sun. And that's the stuff that we see right with our eye. And the sun looks like it does here, visible light. Most of the light that we see, most of the photons, I should say, come out in visible light from the sun. So what is this actually? A pizza. I don't know what the black stuff is on the pizza. I've never had that before. Dates. Anchovies are really good on pizza, by the way. What is this? Okay, part one is correct. What is part two? What is the sun like? How are you? The sun and what kind of light? Okay, it's a guess. Let's say no. Okay, let's say no. on. Okay, correct, no. That's an infrared light, actually. Oh, sorry, I missed it. Okay, sorry, okay, so you get an A. Okay, so you see features, the light coming from the center of the sun. Some of it in this infrared light gets absorbed on the surface of the sun. But the point being here is that the sun looks different in visible light than it does in infrared light. Okay, are you ready for the third one here? What's that?
That's not.
Good. What if it's not the sun, actually? What if I throw a curve? That's the sun in what kind of what? Okay, close enough. Yeah, X-ray. Okay, so a composite X-ray image of the sun, where you see all kind of bubbly features happening on the sun because there's lots of activity. You know, the surface of the sun is a crazy place where lots of flares and stuff like this are happening. So we've seen the sun now in visible light. You know, you can do that if you stare at the sun. I don't suggest doing it for too long. I'm a scientist, so I know that. We've seen it in infrared light, and we've seen it here in X-rays. And we can go across the electromagnetic spectrum. The only technical plot I will show, if this is even technical, this is a spectrum of where the light comes from in the sun. So most of the light in the sun comes from in the visible part of the spectrum, and you can see that corresponds to a certain wavelength for the photons coming out of the sun. Okay, so some of the light comes out in the infrared, and that's what we saw. Some of the light comes out at higher energies or larger wavelengths, or smaller wavelengths, so ultraviolet or X-rays. Okay, so that's an approximate black body spectrum for the sun. Everyone who took my class, several of them are sitting here in the front row. They're experts. They're going to tell you why the sun is not a perfect black body. They know that answer. I'm pointing at you guys because you are the most recent people in my class. Ask them that question. Yeah. Okay. Are we ready for the next one? I hope I know what the next one is. What is that? Okay. Good. Part A. What is the sun? What is that? What are we seeing the sun in? Oh, yes. Yes, Adrian's got it. Okay. So that is the sun, actually neutrinos. So if your eyes could see neutrinos, the creatures in the universe who can see neutrinos, you know, just go find them and they're easy to find. That's the picture of the sun that they would see if they had sort of a coarse pixelation, if their eye was, you know, had about the resolution of modern neutrino telescopes. But of course, it's kind of a false colored image to tell you like where, you know, there's more neutrinos kind of coming from the central regions that are yellow and less coming from the outer regions. But the idea here is that not only can we see the sun in, you know, light, visible light, X-ray light, we can also see it in other types of particles and neutrinos. And this is actually a very interesting story that dates back almost half a century. And we'll go through a little bit of that story today for the next 10 minutes or so. All right, what's the next slide here? Oh, okay. So I'm not allowed to show equations here. I think I made up that rule. But this story actually goes back to the, you know, even before the 1960s. There's this sense that these, you know, I said the photons took, you know, 100 million years or so to get from the center of the sun to us. Okay. Does anybody know how long it takes neutrinos to get from the center of the sun to us? Okay, right. So neutrinos move approximately in the speed of light, right? So they get out there very quickly. So there's this sense that if you could like see the sun and neutrinos, if you go find that mythical creature who has neutrino eyes, you could actually see the sun and neutrinos and see the interior of the sun in some sense, right? So this is pretty profound, actually, right? Right. This is real. You can see sort of the inner workings of what's going on, whereas you can't if you're just looking at it in sort of, you know, visible light, say, where you just see what's going on at the surface of the sun. Okay, so this is so John Bacall actually was a famous researcher in this field who did a lot of the theoretical work to model the sun and predict neutrino fluxes from the sun over sort of a span of, you know, 50 years or so. So, okay. How are we doing here? Oh gosh, now we cut off a little bit. Okay, so how does the sun shine? Okay, so the sun shines basically by in the center of the sun, the temperature is much higher than it is in this room, much higher. Okay. So in the center of the sun, the temperature is hot enough that protons are able to fuse together. Okay, and they're not actually able to, we have a hard time doing that here on Earth. But the conditions are right in the center of the sun that protons can fuse together and sort of they found nuclei. And so this process, during the course of this process happening, you not only sort of make heavier and heavy nuclei in the sun, but you also make neutrinos, and that's where these neutrinos come from. So they come from deep in the interior of the sun, where protons fuse together via this process that we're unable to perform on Earth, or we're able to, but the conditions are right to have it happen in the center of the sun. So ultimately, these are kind of the neutrinos that we're chasing. When we look at those pictures, such as the one that I showed in the last slide, that's where they come from, sort of right in the interior of the sun. Okay, so that is how the sun shines, and that's how the energy gets produced in the center of the sun. Okay, so let's actually take a slight brief detour, like why we need the neutrino in the first place. Okay, so this actually goes back to sort of observing what are called beta decay reactions going back to the 1930s. And so observation sort of, when you sort of try to balance the energy sort of on both sides of the equation, when this beta decay process were observed, the energy sort of didn't balance. Okay, so what that meant was that physicists had to invent a new particle. Okay, and here's a nice quote here from the physicist who, if you will, invented the neutrino. He said, "I've done something very bad today by proposing a particle that cannot be detected. This is something no theorist should ever do. So theorists in the audience, don't do this. Don't propose particles that can't be detected." So the problem is the neutrinos are very sort of quote unquote weakly interacting. Okay, so so he realized theoretically that these particles should exist, right? And it'd be great if they existed and they'd solve a lot of problems, but the problem is we can't actually, they're very difficult to detect, at least back in the 1930s when this was written. However, experimentalists are very ingenious people who can in some cases figure out how to do things that are possible. So the neutrino is actually a mere 20 years later detected in this experiment called the Savannah River experiment. So neutrinos are sort of copiously produced near nuclear reactors. Okay, so basically you put an appropriate detector near a nuclear reactor. In some sense, you can catch some of those neutrinos, not all of them, but just like a very, very small number of them that are coming through. Okay, so here's a scheme about how you catch them on this particular atomic species here. This is a so-called beta decay reaction. What you're doing here is using a neutrino to convert a proton into a neutron. Okay, and sorry, electron. Long story short, neutrino was postulated in 1930s. Theorists said that he did a bad thing. 20 years later, said theorists still a bad person, but I'm still going to detect neutrino, and I've done it. Okay, so there we go. Okay, so we need neutrinos basically to sort of balance the energy in these beta decay reactions, similar to what's happening in the center of the sun. Okay. Okay, so that was detecting neutrinos from reactors. What we really wanted to do was catch those neutrinos from the sun. And the first such experiment that attempted to do that was the homestake experiment, which was constructed in the homestake mine in South Dakota. Anybody from South Dakota? All right. Okay. So okay, so there's a picture of the mine, which is actually above ground because you're kind of in the mountain. You go down and come. So basically, this was just a big tank of chlorine, and what you're trying to do is capture a few of those neutrinos that come from the sun onto the chlorine and turn them into an isotope of argon there. And basically, you're just trying to go down into that detector and collect those isotopes of argon. And then basically that tells you how many neutrinos have reacted with your experiment from the sun. Okay. So there's a couple pictures of the experiment. There's sort of looking down the tunnel in the mine. There's so the main experimentalist here was a guy by the name of Ray Davis. So there's a picture of him swimming in the mine there. I think he got the Presidential Medal of Honor maybe like 20 years ago or something. Okay, so then you can actually count for the rate at which neutrinos are produced in your. It was only maybe like a handful per month that they detected, right? So not like too many. Okay. So this is a small number. It's a hard experiment. Initially, what happened was there's a graph there in the bottom, which you can't really see, but I'll just describe it. They weren't finding enough neutrinos, actually. So, the theorists wrote down the equation and said, oh, you should get that many right there. And Ray Davis was like, oh, sorry, dude, wrong. I've got about a third of those. Okay. And the theorists were like, oh, you go, figure out how you're going to force on the theorist line, everything. And Ray Davis was like, no, about a third. So, okay, so there we go. So that was the first ever kind of solar neutrino experiment. Obviously, it's very profound that they actually detected the neutrinos to begin with, but not coming up with the right answer, that's, is that bad or good? It depended on who you asked. And I should say subsequent experiments actually kind of confirmed about the same story. They weren't catching enough neutrinos. So you can build even larger and larger scale neutrino detectors. So these came around in about the 1990s. So one in Japan called the Super Kamiokande experiment, which they caught neutrinos a little bit differently than other experiments did. They watched them, hit an electron basically, and that electron just gave that electron a lot of energy, and that electron then was recorded in the detector. So here's a picture of the Super Kamiokande experiment. Basically, it's a gigantic tank of water with phototubes standing around it. And they're sort of working on the phototubes in the detector. Okay. So another such experiment was the Sudbury Neutrino Observatory in Ontario in Canada, actually. So these two experiments actually were sort of the the modern sort of generation solar neutrino experiments at the time. And so they actually could sort of test this hypothesis that the original experiment by Davis and friends were missing neutrinos, okay? And so they actually confirmed the original experiment that you're missing some of the neutrinos. Okay, so 40 years plus of experimental activity in this field, and we're still missing the neutrinos. Where do they go? There's that graph there tells you how much you're missing. Okay, so something's happening here to the neutrinos that we don't know. Okay, so long story short. Okay, there's actually 3 kinds of neutrinos. Okay, so these are all the fundamental particles that we know about. So if you took a hammer and tried to break these particles in half, you couldn't. Okay, so these are all the fundamental ones. Try that actually. Don't worry. Okay, so we have 3 types of neutrinos actually. So technically they're called electron, muon, and tau neutrino. Okay. So the sun actually only produces electron type neutrinos in its interior. Okay, it only produces electron type neutrinos. So, but in what was being detected mostly by Davis collaborators were just electron type neutrinos. Okay, so what was happening was that the electron neutrinos were transforming to a different so-called flavor of neutrino as they made the journey from the sun to the earth. Okay, so they happened, that journey happened very quickly, but even in that quick journey, they're saying, I'm going to just change my flavor as I get from there to here. Okay, so what was happening is roughly, anywhere from 2/3 to half of the neutrinos, depending on which experiment was looking, transformed from electron flavors to a different kind of flavor. Okay, so Davis was actually right that he didn't see the appropriate number of neutrinos, right? Because he was just looking for electron type neutrinos. Okay, so and also this is interesting and important because the models which the sun was built upon, how the sun shines, how many neutrinos are produced, those were actually also correct at some level. So everybody was correct. So everybody, gets prized, right, at the end of the day here. Okay. So that actually was a very, very long, that took a long, time, half a century to iron that story out. Okay, I'll spend the last 1 or 2 minutes here talking about the most modern solar neutrino experiments. Okay, so the sort of state-of-the-art solar neutrino experiment is this experiment called the Borexino experiment, which is underground in Italy. And it is actually detecting, it's making super precise measurements of what the flux is of neutrinos from the sun, coming from all kinds of processes that happen in the sun. So this is a little bit of simplification because I'm just showing, neutrinos that are coming just from these original proton-proton collisions, right? But actually, you produce heavier nuclei, and those heavier nuclei then, interact with other heavier nuclei, and they produce neutrinos sort of down the road a little bit. So Borexino is actually detecting all of those kinds of components of neutrinos, like that are coming from all the types of reactions that are happening in the sun. So this actually sort of also, confirms like our understanding of all these nuclear burning processes that are happening in the sun. So this is actually really important. Okay, so there's another way in which neutrinos burn through this so-called carbon, nitrogen, oxygen cycle. Okay, so this is a little bit of a technical point, but one of the really important things that Borexino has done in the past 2 years really is for the first time ever detected neutrinos, basically saying started that came from this process, which started, from burning carbon and nitrogen through this cycle that I'm showing here. Okay, so these have been sort of very elusive, and no one's actually been able to detect these for basically solar neutrino experiments have started, but actually, very small amount of energy from the sun gets produced through this process. And now we're actually identifying the neutrinos that come from this process. So this actually tells you what a great experiment Borexino is. Let's see. So the Earth goes around the sun. Everyone knows that, right? I'm an astronomer, so. But it's not, the Earth doesn't go around the sun in a perfect circle. Okay. So there's a slight sort of eccentricity, so-called, to the Earth's orbit. Okay, so that actually changes the neutrino flux from on a yearly basis, right, by a few percent, because the distance between the Earth and the sun changes by a very small amount. Borexino actually detected that deviation in the neutrino flux on the sort of the yearly periodic deviation, right, just because it's able to measure this flux so precisely. Okay, so okay, and it was actually able to measure the eccentricity of the Earth's orbit and confirm what Kepler found, which is good. Okay, so this is my last slide. So what's left to do, right? So this is solar neutrinos are in some sense the first ever sort of it sort of gave birth to the field of astroparticle physics, if you will, detecting sort of non-photons from astronomical sources. Okay, so astronomers can't decide what the sun is made of. What does that mean? Right, so there's actually a lot of controversy about sort of how, sort of what's the so-called metallicity of the sun, how many heavy elements exist in the sun, what the fraction of them is. And actually, neutrinos can actually ultimately help with this story, especially if we detect those neutrinos from that carbon nitrogen oxygen cycle, which those astronomers call those heavy elements. Okay, and there's lots of controversy about like what that mass fraction is of this heavy element in the sun. So hopefully, at some point in the future, neutrinos start to come in. Eventually, we're getting so good at detecting neutrinos, right, that they're going to interfere with detection of other types of crazy particles called dark matter. Okay, so if you can see, if you were able to see the rest of the diagram, you can see sort of a cartoon of a dark matter particle sort of interacting with the detector. But the problem is, at some point, detectors become so sensitive that they're going to see neutrinos from the sun get in the way of that process. Okay, so neutrinos that used to be this like faint signal that people were trying to detect for many years are now becoming like noise in the background, right, for your experiments, right? So this is actually a particular subject that I'm interested in. So these are just two sort of we're still building these types of experiments. This science is still going on, and I think hopefully we'll have more surprises in the future. But that is all. I'm probably way overboard.
What is the mass for the neutrino?
What is the mass of a neutrino? First of all, is it zero or not zero?
Okay. That's the absolute.
Wait, what do you think? Is it zero or not zero?
At least zero.
Okay. Okay. Good. Is it lighter than every other particle? Or, you know, actually, it's much lighter than any other particle that we know. So the lightest, well, actually, the photon is zero mass. Doesn't count, right? So an electron has a given mass of the number. So a neutrino has a mass about 6 orders of magnitude less than the mass of the electron. And this is actually really so our so-called standard model of particle physics predicts that the mass of the neutrino is precisely zero. So the mass of the neutrino is not zero. I didn't actually go through it, but the fact that neutrinos change flavors, that actually tells you the mass. Okay, so so that's how we know that the mass is not zero. Okay, but really a fundamental question which people are trying to answer is like, why is that mass so much lower than like all the other masses of all particles? If you could figure that out. Yeah. Am I calling names or am I calling people? You're not.
In the Ray Davis experiment, how the heck do they count a handful of argon atoms?
How do they do it? They went in there and they put it's
Takes time, a lot of time, but I don't know the answer to
a it's a little bit technical. Let's talk about it all.
Okay.
What is the practical application? Why do you care? Yeah, I mean, don't like so. Right, we're okay. So, proton fusion happens in the sun. Okay, there's nuclear reactions that happen in the center of the sun. Right, so that's nuclear physics that we use to model the sun, and making these precise predictions for what comes out, the burning processes and how it's happen. Right, that physics actually the same physics that happens on Earth. Everyone can try to somewhat recreate on Earth. Right, so we understand. That type of environment. We can't create an environment, 10 to the 7 degrees Kelvin, right? On Earth at this stage, right? But understanding sort of the limiting cases of our theory, right? And sort of getting to there, right? That tells us, okay, our theory is right, that we understand the neutrinos and these conditions, right? And maybe we can learn, it can maybe tell us something about how to do it, right? So how to get us right.
Could you speak a little bit about what changed in the Texas to discover neutrinos and how we like it to the modern concept of dark energy?
Oh, dark energy, okay. So the question is, what changed in discovering of the neutrinos? I can actually answer that a little bit. So the initial experiments were these so-called radiochemical experiments where they tried to, up over here and here, how they extracted the isotope spark on the tank. Right, so they try to figure out how much argon was created. So those are so-called radiochemical experiments. So the more recent experiments are results of a real-time solar neutrinos. So those weren't real time, and they had to go back every month and say, okay, how many isotopes are on? Okay. Okay, so that's good. So the super Kaitlin Webber, those are so-called real-time experiments where they can actually record events as they're happening. So the neutrino comes in, strikes an electron, and the electron makes a signal in the detector, and they know, okay, got it right there. I can tell you right there that was that had event happen. And so they can actually in real time for count the events. And this another astronomy on tap something to give about this event called supernova 1987A, which is detected neutrino astronomy, because you could actually time the events that came from a supernova explosion, the neutrino events that came from a supernova explosion with the actual observation of that event. So I would say probably the biggest thing is more like real time. That's all.
The methodology of these like field sports that are better. So it's like,
Yeah,
how do you tell people apart?
good question. I mean, yeah, so, yeah, that's the thing, right? So like, so a neutrino or principal manufacturing signal, in some cases as a dark matter particle. Ask somebody else about dark matter. Very fun. So yeah, so really, yeah, I mean, it's kind of, it's a little bit of thought, right? Like, at some point, we're not really there yet in terms of like, okay, well, we're almost there. For the next few years or something. Like, let's say we get to dark matter tomorrow, right? It probably wouldn't be able to make something. Got to see how it's enriched now with that thing on. It's not even even. Yeah, so the answer is it's not.
All right. Y'all ready for some trivia? Oh yeah, Louis, awesome, ain't he? Yeah, I thought suns were made out of like fire and lions. That clears a little bit up for me. Anyways, so raise your hand if you want some trivia cards and some pencils to write down your stuff on your trivia card. Yep, raise some hands.
I think more people could raise some hands. Don't you guys want to do trivia?
There's prizes,
I
right?
see you like 5. Yeah, there's prizes. If you win trivia, you get like a free t-shirt or drink or something.
Yeah.
Keep your hands raised high if you haven't gotten your trivia yet, but you want to play. And if you change your mind later, you can tell us and we'll get you a card. Anyone else trivia? Any takers? Okay, we're gonna get started. Do people have writing utensils? No. A resounding no.
Who needs a
Kevin needs a writing utensil. Okay, let's get started. Just shout and scream if you don't have paper or pencil and we'll help you out. Okay, so the theme for this trivia is telescopes. So question 1, are you guys ready? No? I heard a no, but I heard a yes. Okay. Question 1. In what year was the first telescope made? Is it A, 1508, B, 1608, C, 1708, or D, 1808? Bonus points if you can write down who made it and what kind of telescope it was. Oh, they are? Never mind, those are questions in here.
no bonus point? All right, question number 2. Which type of telescope was invented first? A reflecting one, a refracting one, or a radio one? That's A, B, and C. You guys can figure it out. You're smart.
And if you need us to slow down or repeat questions, just shout at us.
Yeah.
Yeah, go ahead. Okay, question 3. Galileo Galilei invented the telescope. True or false? Is it A, true, or B, false? B. C. What's C? Both? Okay, tricky stuff. I don't know. Don't use Google. That doesn't count.
Question 4. Who invented radio telescopes? Is it A, Isaac Newton, B, Albert Einstein, C, Carl Sagan, or D, Carl Jansky? Oh, Jansky's a cool last name.
Okay. You guys ready for question 5? Yeah. Question 5. The Large Zenith Telescope's mirror is made out of a novel material that costs 1% that of typical mirrors. What is this material? Is it A, gold, B, plastic, C, liquid mercury, or D, glass?
Oh. All right, go
Go
back.
back, go back.
Okay, we're back. So, got the large zenith telescope mirror. What's it made out of? It's cheap. Is it out of gold? Is it plastic or some liquid mercury or glass? What's it made out of? Or is it made out of fire?
It's not an option, don't put that.
I'm not a scientist, so I can say it's made out of fire. I'm not sponsored by anyone. All right, y'all guys ready for question 6? Question 6 is ready for you. Where is the largest ground-based optical telescope located? A, South Africa, B, Texas, C, Chile, or D, the Canary Islands?
If you don't put Texas, you're moving.
Yeah, Texas.
Right. Question 7. How many telescopes are at the McDonald Observatory in West Texas? Is it A, 1, or B, 5, or C, 10? How many telescopes? It's over by Fort Davis. You should check it out sometime, except it's a 9-hour drive because everything in Texas is far away.
Ba-da-ba-ba-ba. All right, question number 8. What did Galileo discover using a telescope? Is it A, craters on the moon, B, Jupiter's moons, C, the phases of Venus, D, all the above, or E, fire?
Okay, question 9. The Hobby Everly Telescope in Fort Davis, Texas has a twin. Where is it located? Is it A, South Africa, these options may seem familiar, B, Texas, C, Chile, or D, the Canary Islands? Or E,
Fire. Okay. You guys probably figured out.
last
now.
one.
You guys seem so smart. Okay, which of these is not the name of a telescope? A, Pumpkin Observatory. B, Large Latin America Millimeter Array, or the Llama. C, Sphinx Observatory. D, Leviathan of Parson. Ooh, that's gotta be, okay, that's a cool one. I'm not a scientist, so I can say I can think any of this is cool.
Okay. That's the last question for trivia. Does anyone want me to go back to an older question? Question 9. Question 9? Question 9. A Hobby Everly Telescope in Fort Davis, Texas has a twin. Where is it located? Okay, any others?
Going once, going twice, and sold.
All right, so that concludes trivia for right now. So, please raise your hands up for your trivia cards to be collected. One of us will grade them, I suppose. We'll announce the winner at the very end of the night. And for now, we're just gonna go on a quick break. How long, Cindy? So we're gonna go on a 10 to 15-minute break and then get back to it.
Tip your dang old bartender, give them all your money. Get to tell them to spend money.
That's a good call.
You know that, you're not good at public speaking, and I'm finding that out right now.
You're fine. You're like. I think there is. No. Well, this is sneak preview.
Oh, wait, the drink thing?
Yeah.
Oh, shoot.
What did we say?
Oh, I forgot about the drink. That's my bad. not
Where
your
did the
bad.
drink go? What? What drink? Here it is. Okay. Oh, where did that go? It's a I had a different tab open, but can you tell people to get their trivia? Oh, over. Just advertise it. Advertise the drink. What do I do? Say it's a galactic cocktail. Yeah, and it's smart.
Those of you going to the bar, do great. There's a new enriched galactic cocktail, and I have heard that it sparkles. So if you would like a sparkling drink, please go order one of the five. And don't forget to add it.
Just want to make sure my video works. This is not me. That's not me. That's not me.
I'm muted right now, so.
Hello? Where's my talk?
Hello, chat.
Huh. Huh.
Whoa. Bro, why is my thing hate me? You mean? I can't say this.
It's just all
Huh?
It's just all judge.
Capillary.
Right. So next up, we got in the news with Nikko. Tolerable alligator. You find them, no real thing. Dog runs before. Anyway, it's Nikko.
Alligators are good people. How's everybody doing? We got a fantastic yeehaw. I don't know if a yeehaw is an appropriate answer to that question.
It's a big fun.
All right, so we're going to talk about some news from this last month. For those who know me, I am an intergalactic astronomer. I tend to look at things that are very, very far away, far out. Somehow this month managed to not have any extragalactic news make it into this talk. Also, sorry, folks. I think that was symmetry after that. I heard a noise in that direction. I see the shields. Also, I've had some sort of tradition of always including a story about supernovae. Supernovae also did not make the list this month. So I'm sorry, but we do have some really cool stories. One that quite a few of you probably heard about in the last week. NASA decided to chuck a $300 million space. So how many of you, I'm looking at some of the regulars here, how many of you remember my in the news talk all the way back in April, where I talked about something called the planetary science field? Does anyone remember this? So the brief rundown is every decade, the National Academies of Sciences come together and basically yell at the government to spend their money at certain bits. And one of the major initiatives of also, I really like to appreciate this cover art. I hope that somebody got paid a decent amount of money to make this. It's pretty awesome. They all have really dramatic names. This one was Enriched and Worlds and a decade looks strategy, but planetary science astrobiology 2023 to 2032 because things got messed up in the last couple of years. So one of the major initiatives I love this quote. One of the major initiatives of the 2020 Planetary Decadal Survey was, in the coming decade, NASA should develop an approach for rapid response, flyby characterization of emerging short warning time, less than 3 years, threats and science opportunities. What kind of threats? Aliens? Unfortunately, it's not aliens. We're talking about asteroids and other near Earth orbit objects. Sorry, maybe in the 2030 Decadal Survey, we'll get something about aliens. So, got a couple videos for you, and a bit of an existential crisis. I'm going to play these. So what you're seeing, we have 51 seconds on this slide. 49 seconds? It went down. So we have 49 seconds on this slide. What you're seeing on the left here is something called NASA DART, which is a spacecraft that was built for $300-something million exclusively to throw itself into this asteroid. What you're seeing on the right, I'll restart it, is the same thing happening from the ground. So left side is spacecraft view, right side is ground view. And so very, very slowly, you see this thing approaching the surface, and all of a sudden, it's dead. And something about this is unbelievably creepy. Just a slow, like 6 seconds per frame, and then it just goes back. And that is the end of that spacecraft. It is deceased. I'll play the one on the right here again. So what you're seeing is this asteroid in the middle, and the spacecraft is actually in that very small asteroid that's right next to that big asteroid. And when you see that big part when it moves again, right about there, that's when the spacecraft impacts that tiny little asteroid that's next to that big asteroid. And it's flinging a whole bunch of rocks and dust and stuff all over the place. Question?
Yeah, so like, what all the dust and stuff just the gravitational pull back into it?
That's a great question. It's too small. There's not enough of it. Maybe eventually given a ton of time, it will, but not like immediately, or even on very short astronomical timescales. So now, you know what? Let me just play these both again while I'm talking. You might be asking yourself, what's the point of this? Why does our tax money go to throwing expensive robots at rocks? For fun, for science. So,
For Bruce Willis.
So if you remember the initiative from the the Planetary 2020 Decadal Survey, they wanted to protect against and respond to emerging short warning threats and science opportunities. And what does that mean? If there was something headed toward the Earth, this is essentially a pilot mission to see if we could shot something at it to make it not kill us. And the also slightly terrifying thing is that we won't know if it actually worked well enough for a little while until we study the remnants. Because you can imagine something's heading at us, we basically chuck a big rock at it in the form of a $300 million spacecraft. We chuck a big rock at it and it goes boom. If we don't break it up enough or push it enough or do any set of a bunch of things, it's still going to come at us. So we need to do enough to it to get it out of the way or blow it up enough so that it won't kill us. I'm not scared. Does anybody have any other questions about that before we move on? Am I the only one who had a bit of an existential crisis seeing that screen go red? Okay, thank you. Moving on to some other stories. Some honorable mention headlines. We're gonna get to look at some pretty pictures. So I like to call this the floor is lava. This planet is about the size of Earth, about twice the diameter of Earth. And it's orbiting very close to a relatively sun-like star. And by very close, I mean its period, its orbital period is effectively its year, is 1 Earth day. It is whipping around this star real tight, real hot. The surface is something like 2,000 degrees Fahrenheit. So although it is Earth-like in size and terrestrial in nature, it is a ball of lava and nothing like us to live there. Sorry, science fiction writers, if you want to write about some alien life form that can live in lava, have fun. What's also really cool about this is that there's a Jupiter-sized planet that's orbiting just outside of that. It has a period of like 2 days. So this is the first system like this that has been seen, where you have something called a hot Jupiter, basically a Jupiter-sized planet that's really close to a star, with an Earth-sized planet that is inside at this close of an orbital radius. One thing that's amazing to me about this is that if you plug in these 3 bodies, so the star, big planet, and little planet, into essentially Kepler's laws for a three-body motion problem, this orbit is actually stable, which is nuts to me that you have 2 things that are that tight to a star, and one of them's the size of Jupiter, and it's a sun-like star and Earth-like planet. Earth-like, other than the fact that it's 2,000 degrees on the surface, and it's just stable. It's just gonna chill out there for quite a long time. So that's pretty nuts. This picture is ridiculous. So those of you who have also been regulars and have seen me talk a lot, you know that I work a lot with something called the James Webb Space Telescope. You might have heard of it. You will never escape the James Webb Space Telescope when I'm giving in the news. You might escape Excel, you might escape supernova. You will never escape them. I'm glad it makes one for this talk. What you're seeing in the picture is Jupiter as seen by the University in mid-infrared light. And you can see the aurora of Jupiter, just like we have aurora on Earth. Aurora is the plural of aurora. It's very Latin. So you see these kind of blue things on the north and south poles. That's essentially the same thing that aurora borealis and aurora australis are on the Earth, but it's on Jupiter, as seen by JWST. It's really pretty. Go look at other pictures. And you can also, if you squint really closely, maybe a couple pictures on this. You can see out here to the left, there's at least 2 moons that you can see. And it's pretty awesome. You can get a nice dust ring in the middle. That's probably really hard to see from where you guys are in the audience. Okay. Our last story of the day, we're going to talk about a group of authors who harassed an innocent star for no reason. So a decidedly unremarkable star was discovered orbiting a what? Anybody? Orbiting a black hole. So this paper, which came out about a week ago, found something very similar to the sun in size and chemistry and temperature, whatever you want, orbiting a black hole. So you're like, what? How? 1, how? 2, how do they know? So one might see something like this. If you have a big thing orbiting with a little thing around it. You have a big thing in the middle, which is kind of doing this, and a little thing doing this. But if you look at this thing, so in this case, think of something like the Earth and the Moon, or the Sun and the planets, whatever. In this case, you see this. So you just see thing just doing this for no reason. So there has to be something there. So if something moves, if something moves in a circle, there has to be a force pulling it into the middle, right? Everybody learned this in high school physics. And so what is that thing? If you can't see it, it's not light. So it might be a black hole. How do we know that it's a black hole and not a bunch of other things? Well, throw in, let it fit to a bunch of models, see that nothing else works except for a black hole. So now, what is this thing like? It's a G-type star, which is the same as the sun. It's got the same temperature as the sun, like exceedingly close to the same temperature as the sun, 5,800 Kelvin. And it's, order magnitude the same mass as the sun. The black hole, if you plug in orbital equations, has a mass about 10 times that of the sun, and it is the closest known black hole to us, about 500 parsecs away, order magnitude, 1,500 light years away. This is pretty nuts. There's a couple questions here. How do we know that it's a black hole, not something else dark? How do we know that it's one black hole and not multiple black holes? The answers get pretty intricate and subtle. Basically, you can chalk it up to, if it was multiple, then it would look like it was multiple. It does not look like it is multiple. So if you look at things like the spectra, if you look at things like the spectra and the orbital path, it doesn't look like it's multiple things. We see perturbations that are not characteristic of one single larger mass individual. And so I'm going to end here by saying, this was discovered by Gaia. It has, I also like to talk a lot about naming conventions when I'm up here giving interviews. So you'll see me talk about like exoplanets and things that have names like WASP, 403, C, B. This had the name of Gaia BH1 because it is the first black hole confirmed by Gaia, and I think that's just really pretty. The other question, which I'll end with, is how many more of these are there? And so with future data releases from Gaia, we expect to see dozens, order of dozens of these things, which I think is going to be pretty cool. We've only seen one, so we're doing statistics about one object, but hopefully we'll see more soon. And I will end this in the news by saying, if there are any science fiction authors in the audience, you just got 4 stories that are really good science fiction topics. Please write 2 books. That's in the news. Thank you very much. I would also like to say that when I was making these slides, having to build this slide with this animation going, you kind of just end up staring at this thing, and you just get wrapped into a bank of staring at this stupid white little dot. That happened to me multiple times in the last one. Thank you.
Is there an estimated time for when the data will come back on the version of the actual?
Order weeks.
Yeah, it's already gonna take about 2 weeks.
So within the next month or so, we will know if we just wasted your.
No, it's not a waste, it's through theory.
If there's data, a null result is still a result. Write a paper about it.
We also already have to confirm these 2 weeks.
Really?
Yeah.
Okay, well, it has been,
That's like 4 hours.
yeah, it has been what, like 48 hours when it was sometime yesterday?
But like 4 hours.
Yeah.
For the mass sensitivity, now it's like 15 weeks.
So something,
Yeah.
to some degree.
This was
Not
like,
intended.
well, like past that, like, you're gonna get some results.
Great. it was a transit. Yeah. Sorry, so Maeve asked, how did they detect, this thing? So actually, so the hot Jupiter, the other big thing that's orbiting around this relatively sibling star, they detected that one first, I think it was a few years ago, and then relatively recently, sometime in the last or so, I think, they did see transits of the little Earth. Do we have time? Okay. Last one.
So in my head, what I'm imagining that it's kind of like research and you one of those things that is gonna look like it's the black hole and then it's the orbit and it's a bit smaller and smaller, so it's like something in the black hole.
So short answer is yes. Long answer is it depends on what kind of time scale you care about. If you care about like lifetime of the universe, maybe not. I'm not sure of the exact specifications of this orbit, if it's losing energy rapidly enough for that. But yes, inherently, yes, everything would do that eventually. So there's not really anything else close to this, which gives rise to interesting questions about how something like this forms. We think that basically this star was just chugging along in space and then got caught up in this black hole. And so since there's nothing else around it, unless some other event like that happened, no, but perhaps. Thank you.
Okay, our final speaker of the night is Kaitlin Webber. Come on up. Kaitlin Webber is a third-year graduate student at Texas A&M University in astronomy, and she's an expert on Milky Way observation. She's going to talk to us about observing.
We just not have a lot.
Okay, hi everyone. So I'm Kaitlin. As Addie said, I'm a third year graduate student and I'm an observational astronomer. So my talk tonight is red lights, long nights, and I'm going to be going over what it's like to go observing. So for this talk, I'm going to be focusing on McDonald Observatory because that's where I've done most of my observing. So McDonald is located out in West Texas in Fort Davis. It's about a 9-hour drive from here. And on site, there's 5 telescopes. So the first telescope that they have there is 0.8 meter telescope. And so this is the dome. And the mirror for this telescope was actually made from material left over from when they were making the 2.7 meter. And then this is what the control room looks like. And nowadays it's mostly used for outreach programs. And so the next telescope is 0.9 meter. And this telescope was designed for photometry, so basically just collecting light and then producing pictures. And it's also used for outreach, and that's what the telescope looks like. So the next telescope is a 2.1 meter autostroop. And this one was the original telescope at McDonald, and the dome actually contained all of the facilities. So it used to have the living quarters for the astronomers, and now they've turned it into a bit of a museum / library. And so the next telescope is the 2.7 meter Harlan J. Smith telescope. And so this is the one that I use when I go observing. And so the primary here is 2.7 meters and weighs approximately 7,800 pounds. And then the telescope tube is 12 feet in diameter, 32 feet in length, and weighs approximately 170 tons. And there's a person next to the counterweight as perspective to how large this telescope is. And it's actually roughly the same size as the Hubble Space Telescope. The tube is slightly smaller by like 2 feet. And then a fun fact, one time someone went up to McDonald and they brought a gun with them and they shot into the mirror of the telescope. And so there's actually 6 holes in the mirror that are kind of hard to see, but there's little black specks there. So it didn't break the mirror. And so they decided to just smooth over where the bullets went in, and it works fine. So if you tilt the telescope down, you can actually look into it and see where the bullet holes are. So the last telescope that's at McDonald is the Hobby Everly telescope. So this is the 10-meter telescope, and it runs TETDEX, which is searching for dark matter. So we have all of these great telescopes, and so the question is, how do you get to use them? So in order to use them, you have to write a proposal and you submit that proposal. So the first step in that is to think of a great idea. So the telescopes that are approximately 2 to 3 meters, they cost $6,000 a night to run. And so you have to come up with a really great research idea that the telescope can help you answer. And it has to be approximately $6,000 worth. So the next thing that you need to do is write the proposal. And then you wait. So once you submit your proposal, you have to wait for the committee to meet, and they go over all the different proposals and they decide which one's worth $6,000 a night. And then hopefully, if they like your idea, you get awarded the time, and then you get to travel to the telescopes. So now I'm going to take a quick detour for a little bit of background information. So on the 2.7 meter, there's the tallest spectrograph. And so how the spectrographs work is that you have your star, and that sends light down to the telescope. And then there's either a prism, or for on the 2.7 meter, it's a shell grating. And so that splits the light into the spectrum that then we're able to look at. So once you get to the telescope, there's a lot of things that you have to do. So the first afternoon, what you have to do first is prepare the spectrograph room. So what you do is you go down into this dark room, and it's kind of hard to see. You really don't want light down there because it absorbs it and then it can affect your images. And so you have to remove all of these little mirror covers. And there's probably about 12 of them down in this dark room. And if you don't remove all of them, you will find out at some point, because you'll just get darkness. That is all you will see. And it's happened before, it will happen again probably. So you have to be very careful to make sure that you remove all the mirror covers. And so then the next thing that you have to do is fill the dewar. So in order for the spectrograph to work properly, it has to be kept at very low temperature. And so for that, we use liquid nitrogen. And so as you can kind of see, we fill the dewar with the liquid nitrogen, and then the hose is actually like freezes over while it's going in. And then most important thing is you have to turn off the lights in this room. So then the next thing that you do is go up the stairs to another little room that holds more of the spectrograph. So on here, there's a little rotating wheel of different slits, and those are the slits. So you want to choose what size you want that will suit your targets. And so you just rotate that to the correct one. And then there's more mirror covers that you need to remove. And then there's also that white tube is the solar port. And so when that's open, like it is in this picture, it can allow sunlight in. And so you could actually take images of the sun, and then you can close it later on during the night. So the next thing that you have to do is calibrations. So when you observe, this is what we get as far as data out. And so as you can see, it kind of just looks like a whole bunch of lines. And so the calibrations allow us to adjust the position of the spectrograph so that we can know exactly what each of these lines are. So then usually you get to take a break, eat dinner, and then once it approaches sunset, you start your night. So the first thing that you need to do is check the weather. If the weather isn't good, then you can't observe. So some of the things obviously is rain. if it's raining or if there's any liquid anywhere, you cannot observe, you can't open the dome because it will ruin the telescope. And so then the next thing is the humidity. So usually if it's under 85% humidity, you don't need to check it. And they have little monitors outside on the dome of the telescope that monitors all of these things and tells you. And so if it's greater than 85%, you actually have to go out onto the catwalk and feel the dome, make sure that there's not any water along it. And if there is, can't open the telescope. So the next thing that you have to think about is dust. So there's too many particles in the air. You can't open the dome because they could come inside and then scratch the mirrors, and we don't want that. And then finally, wind. If there's too much wind, it can shake the dome and then also ruin the telescope. So, yeah. So once you check the weather, then you can finally open the dome. So this is the 2.7 meter telescope, and the dome here is open. And so what you do is you pull down a button and two doors open up. And then you have these things are the wind screens that then you can, if it's not windy, you can lower them completely. And it's slightly windy, but still in a safe zone, you can raise them slightly to protect the telescope. And then the most important thing that you have to do during this time is watch the sunset. So you traveled 9 hours or more to get to this observatory, and you are ready to go, and so you have to watch the sunset. Okay, yes, this video, okay. Not going to work, okay. How do I make it big again? Okay, so here's some pictures of the sunset. So once the sun starts setting, then it gets dark and you're able to start observing. So I'm going to take another detour on how you actually operate a 2.7 meter telescope. So this is what the control room looks like. So as you can see, there's two large screens with about 1 million different tabs open of everything that you need to control the telescope. So one of these screens here on the left is actually the telescope control. So on your computer, you enter the coordinates that you want of your star that you want to look at, and then you tell it to go to there. And then you have to run down and go out into the dome floor to the controller that's in the right picture. And there you hold down another button and move the telescope. So the #1 rule when you're observing is don't crash the telescope. So there's at least 2 different tiers, and then the telescope itself that you have to always be watching to make sure that it doesn't hit. And usually the computer is fine and it knows where it's going, but sometimes computers have minds of their own, and so you have to make sure that the telescope is going where you actually told it to go, and not just like flying off somewhere, because then it'll hit the side and then you have to take a call of shame. And you really don't want to have to do that. So yeah. So then you finally get to start observing. So the first thing that you need to do is pointing. And so to do this, you have to use what we call an SK5 star. So this is a super bright star that we know very well where it's located in the sky. And so with this star, you point at it and then you zero out the coordinates so that the telescope knows where to go throughout the rest of the night. And so then after that, you can go to a standard star. And so again, this is another just really bright star that we know a lot about. And with this, you can actually focus the telescope. And so you get the star into your little box that I'll show you later. And then you run a program and it tells you whether anything needs to be adjusted, and you just automatically adjust that. And then its focus. And so then, oh, sometimes you get to make decisions when you're in charge and observing, and so you decide to focus on Jupiter because it's super bright, and so then you get cool pictures like this. Yeah. So the next thing that you get to do is actually finally start observing your targets. So you have your target, you put in the coordinates, go out with the telescope, and then you get something like this on the left. So the telescope knows the general area of where it's supposed to go, but it doesn't know exactly which star it's supposed to point at. That's up to you. So how we do this is we have a handy website, which is on the smaller computer screen on the right picture, and that gives you a little star chart, and your star is in the center of that. And so then you get to play a fun matching game and determine where in the field of view of the telescope your target is. So for example, on the picture on the right, it's kind of hard to see, but there's the two brighter stars in the bottom, and then in the yellow box is another bright star, and then there's a couple other stars on the right hand side. And that matches what we see in the picture, and so we're able to move the telescope. We tell the telescope to move the yellow box onto that star, and then that is on our slit, and so the light is coming through to the spectrum. So then you, at this point, you can usually start your exposure. For me, I look at fairly faint stars, and so the exposure lasts like 1 to 2 hours. And so there's not much to do during this time other than sit and just watch and make sure that the telescope is more or less doing what it's supposed to be doing. And so during this time, you always have to be watching the weather because it can change rapidly. And yeah, you could have to close the dome at any time. And then another important part of observing is enjoying the views. So McDonald is a dark sky area, and so you get really great pictures. So this is actually the Milky Way. This time of year, you can go out and see it really well there. And then there's Orion over the 2.1 meter dome. Here you can see the Pleiades up in the upper part of this picture. And then again, this is just the Milky Way over the visitor center at McDonald. So then you repeat this process for all your targets throughout the night until the sun starts rising. And then that is when you can close the dome and watch the sunset, and then make sure that all your data is good and downloaded. And then you finally get to go to sleep at about 7 a.m. And so at McDonald's, they have the astronomer's lodge, very nice. Yeah. So you can actually go and visit McDonald Observatory. It is a long drive, but it is very much worth it for the dark skies. And so they have a visitor center that's open Tuesday to Saturday, 12 to 5. And then on Tuesdays, Fridays, and Saturdays, they do a solar viewing, a guided tour, and then a star party at night that are really great. So that's my talk. And are there any questions?
Is there like an observatory staff for advising you to this let you know?
Yes, yes. So McDonald is actually a fairly unique observatory nowadays where you get to do most of it on your own, but there is a night staff on hand that usually they help you get set up, and then they'll usually go away but be on call if anything happens, such as crashing the telescope.
What was your idea?
Sorry, what?
What was your idea in your?
Yes. So I looked at, I do chemical abundances of stars in ultra-faint dwarf galaxies and stellar streams. So the last time I was observing, we were looking at stars in the G1 stream and using the high resolution spectrograph to get the spectra, and then we can analyze what elements are inside those stars. Oh, yes. So when you're observing, you really want your eyes to be adjusted to the dark because you're living in the dark. And so we use red flashlights usually, and like in the visitor center, I guess they're not super reddish, but they have red lights everywhere because your pupil doesn't dilate as much with red light versus white or blue lights. And so it keeps your eyes better adjusted to the dark.
When you think of the spectrograph, like is all of the light from also during the spectrograph, like, or like it's possible to take like image and the spectrograph at the same time.
Yeah, you can do both.
Okay.
Yeah.
Is it like a beam splitter or something? How does that work? Like it's the light goes like emitter. It's spectrograph.
Yeah, so like it goes to the CCD and then you can take like, because I don't know how to explain it exactly. But a CCD is a charged couple device. It measures the photons. So like you have this happening at the same time as you can see just like what the telescope is. Yeah. I don't know if that.
So it's like some light is going straight at the like imager. Something that's like directed out.
Yeah.
How would you deal with scattered clouds?
What?
How would you deal with scattered clouds?
Good question. So the question was, what would you do with scattered clouds? So usually you have a long list of targets, and so if you're lucky, some of your targets won't be in the part of the sky where there are clouds, so you just move to the other part. This telescope is actually fairly good. If the clouds are thin enough, you can usually see through it and still get a high enough signal to noise. But if you can't, unfortunately, then you just have to wait it out.
Have you encountered this?
Yeah, so that's there's like just an automatic program, and so you take it to a star and then take it slightly off the slit, and then it just like runs the program itself and decides whether it's focused or not.
Is it like looking at like hydrogen lines, something like this? Or
So we do that as well separately, but that's not actually calibrating it. So we do what's called like flats and biases. And so that's just like looking at a lamp, and then that gives us the spectrum that then we can use as comparison. Yeah.
Why did that shoot here? You know?
Who knows? There's about like, I've heard 3 or 4 different versions of the story. Yeah, no one really knows why.
Okay.
It's Texas.
Sure.
How can that accept the telescope with 6 bullets?
That's a fair point. So we just want as little damaging the mirror as possible. Yeah, I guess in theory it would do a lot less damage than the 6 bullets, but yeah.
Okay, give it up to Kaitlin. Okay, so for our last little ditty of the night, we're gonna go over the trivia answers and then announce the trivia winner. Not bad, not bad. One sec. Yes. Spoilers. Okay. All right. So question 1: in what year was the first telescope patented? Did you guys answer this one? Any guesses? Oh. It is 1608. Okay.
All right, so which type of telescope was invented first? Was it reflecting, refracting, or radio? Well, guess what, guys? It was refracting. How'd you not know that? That's so easy.
Okay, question 3. Galileo Galilei invented the telescope. False? Any truths? Any Galileo fans?
Is it true? True?
No?
Okay, no. Okay,
That is false.
it's fake.
It was actually Hans Lippershey. I don't recognize that name. So yeah, Galileo improved the design and was the first to use the telescope to study the objects in space. I actually thought it was Galileo, so now I feel really bad for Hans Lippershey, but now we all know. So tell your friends, don't let Galileo take all the credit.
All right, who invented radio telescopes? Maybe it was Carl. Yeah, it's Carl! Yeah, dude! Okay, sorry. That's a big moment for me. Okay. It's Carl.
But specifically chance to not say again.
Who cares? It's Carl!
Okay, question 5. The large Siemens telescope sphere is made out of what?
Fire!
Unfortunately, it was liquid mercury. That's pretty cool, actually. I didn't know that would cost 1% of the typical telescope. Oh, they don't have to smooth it. That's very interesting. Okay, you learned something new. All right, question 6.
Where is the largest ground-based optical telescope located? Everybody knows this. This is so easy. Come on. Oh, I messed it up. I made it worse. Fire. Fire. Yes, this guy wins.
Close
Oh.
enough.
It's the Canary Islands. I don't pronounce things.
Question 7. Who was paying attention? It was 5. You guys are good.
All right. What did Galileo discover using a telescope? Was it craters? It's not caterers. That's craters on the moon, Jupiter's moon, all the phases of Venus are all the above. It's fire, guys. Press the slide, and it's fire. Ignore that as a typo.
Question 9. The Hobby Everly telescope in Fort Davis, Texas, has a twin. Where is it? I'm not hearing any very confident answers. Someone, the person who made the trivia and saying a particular answer, I'm in South Africa. You know where it is? South. All right. Question 10.
Which of these is not the name of a telescope? Yeah, dude, all of these should be the name of telescopes, especially the long one. Okay, whatever, press the button, let's figure it out. It's the pumpkin one. Wow, well, we'll change that. We're funding the pumpkin telescope.
Okay, I just point out this. It's not, well, they all are, but this picture looks especially cool. And there's an elevator at the back of it that goes all the way down to the base and you just take it up. I don't know what oh, wow. Okay. It's a what? The bottom picture is the light in the parking lot and all of that makes sense. The picture and the location. So, okay, drum roll, please. While we announce the winner.
All right. No, that's the kangaroo can't jump backwards. It's Serene. It's Serene. Get up, get up.
Please see Silvana Delgado back there to discuss your prize. And I'd also point out we have a runner-up, and it is that man over there. That took a lot of time. We'll get her out of the All right, so that concludes our 51st Astronomy on Tap. Oh, wrong way. That's science.
That's a bunch of code.
Sorry. Wait, pause. I'm trying to find the announcements. I'm so sorry. Okay, this is it. This is it. Okay. Yeah, okay, so our next event is October 26th, 2022. Please wear a costume. If you are so inclined, we'll have a costume contest.
Fourth Wednesday.
It's the 4th Wednesday of every month. We got a new drink. You can support us by donating in our donation box or on Venmo at AoT BCS. If you donate $15, you get a t-shirt, you can check them out over there. If you donate $10, you get a mug, and please don't forget to tip your bartenders. Thank you.
Did it. You did it. You did good. You did the work. Dang, I did it.
Last one, and also don't forget to try to use
That man over there next to Silva. So, yeah, so my last year of undergrad, actually, for like half a